Lesson 4, Conditional Probability. This lesson will teach me to find conditional probability, use conditional probability to determine independence. Alright, so as previously discussed, conditional probability is the probability that event has occurred given, which is what this symbol is right here, given that another event has already occurred. The probability that event A will happen given that B already has happened is the probability of A times B over the probability of B. As discussed, those numbers, that idea there is the same. The probability that event B will happen given that event A has already happened given that A has already happened, so this says the probability of event B given that A has already happened is the probability of A and B over the probability of A. And again, the fact that A is on the denominator. So all of that has been previously discussed. The new part today is the idea of using conditional probability to determine independence. If events A and B are independent, the probability of event A is not changed by event B. So we talked earlier in the unit that independent events very often deal with replacing. You're looking at your closet and you're trying to decide what to wear. You take out a shirt, you put it back, it resets the probability. So the probability of you picking some other type of shirt is now back to the original. Dependent events are where the probability of the second event or the first event has affected the second. So something like, again, thinking about your shirts and thinking about what to wear, and you take a shirt and you hold on to it, and then you pick a second time, the second event has been affected by the first. So we have a couple different ways to determine independence. The first one was discussed in lesson number 2, where it says the probability of A and B is the probability of A times the probability of B. So if events are independent, then this is true. Well, dealing here with conditional probability, there is now another way. If you were to take the conditional probability, or the probability of A given B, if you calculate this probability and it equals the probability of event A, so for instance, you calculate this problem to be 3/5, and then you calculate this probability to be 3/5. If these are identical, what that means is that event B taking place didn't impact event A. Think about what this says. The probability of event A given that B has already occurred. Well, if A and B are two events that have nothing to do with each other, then B's probability, or whatever B did, isn't going to influence A, and their probabilities will be identical. Similarly, the probability of event B given that A has already occurred. If you take the time and you calculate this probability and you get a number, if it equals the probability of event B, then that means this second event, this is actually the first event, the thing that has already occurred didn't influence the probability. So again, meaning the second event didn't influence the first, that these will be different events, which means they're dependent or not independent. So the way that I've chosen to kind of go about setting these up for you is, so here's an event, rolling the dice. So here is our 36. We're rolling 2 number cubes. So first number cube, second, first, second, first, second, so on and so forth. It says let A equal rolling a 3 on the first die, and let B equal the sum of 8. So what I've done in this chart is I'm trying to set you up to find all the different possible probabilities that we can. We know how to find probability of single events. We know how to find the probability of and we know how to find conditional probability. In order to determine independence, you're going to have to then select those that apply. The purpose of this table is to lay out the process for you. So let's begin. The probability of event A is the probability of you rolling a 3 on that first number cube. How many do we have? 1, 2, 3, 4, 5, 6 out of all 36 possible combinations. So 6 out of 36 is the same as 1/6. The probability of event B. So the event B is the sum of 8. Well, what sums to 8? Let's see. This does, this does, this does, this does, and this does. So 1, 2, 3, 4, 5 options. So there are 5 things, 5 combinations of these dice that sum to 8 over all 36. The probability of A and B. So this is saying the probability that you get a 3 on the first and it has a sum of 8. Because of this word and, we're still looking at all 36. We're not limiting the sample space like we would with conditional probability. So how many have a 3 on the first and have a sum of 8? 3 on the first and a sum of 8. It's going to be this one right here. There's only one of them. Let's keep going. Conditional probability. What you're doing here is you're finding the probability that there's a 3 on the first given that you already have a sum of 8. So what we're doing here is we're limiting the sample space to those that have a sum of 8. So those are these red ones. 1, 2, 3, 4, 5 have a total sum of 8. Of those 8, how many have a 3 on the first? Just one. All right, probability of event B happening, meaning they have a sum of 8, given that event A has already happened, meaning given that you've rolled a 3 on the first dice. So how many have a 3 on the first? 1, 2, 3, 4, 5, 6. So we're limiting that sample space to those 6. How many of those 6 sum to 8? One of them. So here are all of our probabilities that we know how to find. If you look back here, it says, if events are independent, then the probability of A times the probability of B equals the probability of the combined two. So let's check it. If events are independent, then the probability of A times the probability of B is going to equal the probability of A and B. Well, we found the probability of A, it's 1 over 6. We found the probability of B, it's 5 over 36. And we found the probability of A and B to being 1 over 36. Are these things equal? It turns out that they're not, so I'm not going to select this option. Let's check some of the others. It says if the events are independent, then the probability of A given B should equal the probability of A. So let's check it here. Does the probability of A given B, meaning we found it to be 1 over 5, does it equal the probability of event A, 1 over 6? No. Not going to select that option. Let's try another one. The probability of B given A we found is 1/6. Does it equal the probability that we calculated for B, 5 over 36? No. Events A and B are independent. No, they're not independent. If they were, we would have selected the first, we would have selected the second, and we would have selected the last. These events, because we weren't able to select those, are dependent events. And think about that for a moment. They will be dependent events because of the idea of the sum, that this 3 is going to influence that sum of 8. So let's try another example. 65 students were surveyed about watching sports on TV. 50 students said that they like watching football. 20 students said that they like watching soccer. Of those students, there were 5 who like both. If a random student is selected from the survey, find the probabilities below. First thing I'm going to do here is draw a Venn diagram. I have people who watch football, and these people are those that like soccer, and the ones in the middle like both. So there were 50 students who liked football, 20 who liked soccer, and 5 who liked both. So what we really have here is if you think about this 5 as counting in both, There are really 45 students total who like watching just football, and 15 students who like watching just soccer, and these 5 that are in the middle. If you were to add up these numbers, 45 plus 15 plus 5, there's the 65 as stated originally. So the probability of event A is the probability of somebody liking to watch football. So out of all 65 people, how many liked watching football? There were 50. Probability of event B is the probability of a student liking soccer. Out of all 65 people surveyed, how many of them liked soccer? There were 20 total, the 15 who liked just soccer and the 5 who liked both. Here we're trying to find the probability of A and B. Again, out of all 65 participants of the surveyed who liked both football and soccer. These are the people that are being overlapped. There were 5. The probability of A, oh, there's my Venn diagram. The probability of A, these are people who like football, given that we're looking at those people who also like soccer. So we're limiting the sample space by those that like soccer. So there are 20. How many people like football given that they also like soccer? Well, that's the probability of people liking football and the probability of people liking soccer all over those who only like soccer. So it's 5 over 20, which is the same as 1/4. The probability of B given A. Well, the probability, event B is those people who like soccer, given that we're looking only at the people who like football. So what we're doing here is we're finding all of those people who like just football. There are 50 people who like football, and we're finding the people who like both football and soccer. There are 5, which is 1 over 10. So again, let's go through these different things to check. If an event is independent, then this should be true, this should be true, this should be true, so then we would also pick that. So let's compare. If we look at our probability of A given B, we found it to be 1/4. Does that equal what we got for the probability of A? Well, we didn't reduce 50 over 65, but it's definitely not 1/4, so no. Looking at the probability of event B given A was 1/10. Does that equal 20 over 65? You can use your calculator if you need to, but no, they're not equal. So are these events independent? No, because these equations did not hold true. So these events have to be dependent. One other way, the probability of A and B, which is this symbol, we got to be as 5 over 65. Does it equal us multiplying this together times the other? I bet it doesn't, and it's because they are dependent events. The reason why they're dependent events, look at this overlap. The probability of one and the probability of the other are connected because of the overlap. So they are, in fact, dependent events. All right, here's another one. So, looking at my timer, I hate to do this to you all, but I have 50 seconds left. So I'm going to stop this video and then I'm going to start another one. That way I don't cheat you all on explanation. So here's me ending this one. Second one is to come.